Okay, so for here, what we're going to do is we're going to do something similar to a previous problem. And so it's 15 over here. I'm going to move this height over here, and I'm going to move this height over here. So we form right angles. This is 50, so this will be 50 as well because this is a rectangle. So now we can use Pythagorean. So using Pythagorean, we get that this side over here is 20 squared minus 12 squared, and the square root of that, so that's 16. And this side would be 15 squared minus 12 squared, square root of that, and you get 9. So now we know that so now let's look at the formula of a trapezoid, like the area of a trapezoid. It's half b1 plus b2 times h. We know b1 is equal to 50, b2 is equal to 9 plus 50 plus 16, which is equal to 75. And then we know h is equal to 12. So from that, we plug it in and we go 50 plus 75, and then times 12. So it's 6 times 125, I believe. Yeah. And that would be 750. So our answer is 750. So that was a really quick solve once you have that insight on what to do, because of like a previous problem that we did, or in general, just like for trapezoids, try to drop altitudes as much as possible and try to find like use parallel lines and rectangles to your advantage. Okay, so now we'll venture out into something called 3D geometry, which is basically dealing with three-dimensional objects, and many of you are familiar already with some 3D shapes like cubes, cones, spheres, which are basically like balls, and things like that. A useful technique is to work towards finding the right 2D cross sections to take, because our human brain is comfortable working with two-dimensional figures, labeling them and things like that, working them out on paper. So what you want to do is when you get a 3D problem, break it down into 2D figures, cross sections. Basic cross sections are things that you cut, like a slice that you cut, and then try to work on those. So for example, a ball of center C and units, 2 units radius has points A and B marked on the surface. Distance AB, so actually it's AB, is 2 units. Find the distance between C and AB. So for this example, we have the diagram drawn over here. So this is going to be C. And then here's our I guess diagram. And what we're doing is we're taking a 2D cross section, and what we're doing is the ball, we're cutting it down the like one of the center slices, and such that it goes from A to B. So A and B are both on that circle. So this is a convenient cross section that we have. And now we're trying to find the distance between C and AB. So that would be just equivalent, now that we have a cross section, that would be just equivalent to finding the height from here all the way down here. And so that's basically how you would try to solve it. And in that case, that would be as simple as breaking it down into a right triangle. And then you do square root of 2 squared minus 1 squared, which is equal to square root of 3. So its height is square root of 3. And so that's the distance. And so if you look at it, you can use Pythagorean theorem, and that's what we're going to use. Just ignore this for right now, unless you know what 30, 60, 90 is already. And you can use Pythagorean theorem and find out that x, or the distance we're trying to find, is root 3. Now here, the main takeaway in this question is trying to find the correct cross-section, 2D cross-section. And the one that worked out for us is the one that contained A, B, and C. And so you want to try to find cross-sections that contain most of the points or lengths that your question is talking about. And you want enough cross-sections such that like almost every single important point or plane is covered. So there are cases like a sphere is inscribed in a square pyramid, although AMC08 generally sways away from it. Spheres are clear of these kind of questions, but again, having a 2D version of it is I can't stress how important it is for 3D questions because our brain just doesn't visualize things very easily. And so, for example, in this case, we see that they're taking a cross section this way. So that's kind of the point of this. In general, these kind of questions require a lot of thinking. So if you can't think about a good cross section to cut during the actual contest, you should skip the question and come back to it, because 3D questions, like I said, take a long time to kind of think about unless you get it right away. And so there's no general strategy necessarily other than the main one, which is like taking through 2D cross sections and trying to figure things out. And you want to try to use all the information that they give you in the questions. So now let's look into spheres, cylinders, and cones. So this is stuff that actually shows up on AMC8. The volume of a sphere is given by 4/3 pi r cubed, where r is the radius, r equals radius, and the surface area, which is, if you were to wrap foil around the ball or the sphere, what would be, the area of such a foil piece? That's called surface area, basically. Cylinder is a little different. So it's pi r squared h, because there's a height to a cylinder. So that's the area volume. Volume means basically if you were to fill it with water, for example, how much water would you fill it with? And surface area, like I described before, what basically if you were to wrap foil around it, what would be the area of the foil? And that would be given by 2 pi r squared plus 2 pi r h. And lastly, a circular cone. So the image didn't show up properly, but it looks like this. Yeah. So that's how a cone looks. And just so we have things looking good, I'm just going to redraw this cone right in this box. R and H S. Okay, there we go. And B is basically the base area, or pi r squared in our case, and because of the cone. So yeah, so these are the three main ones, and I would really take note of this slide in particular, which has all the formulas and the diagrams of the circle, of the sphere, the cylinder, and the cone. And as you notice, there's a lot of pi going on in this, and that's because all three of these are very circular in nature, and AMC8 loves to ask about these, so it's important to memorize these ideas. So now there's an example. Jerry cuts a wedge from a 6 centimeter cylinder of Bologna, as shown by the dashed curve. Which answer choice is closest to the volume of his wedge in cubic centimeters? Okay, so I think the diagram didn't show up correctly again, but I will draw it out. So for everyone's reference, pardon me if my drawing isn't the best, but okay. So, okay. So that's our drawing. This is 6 centimeters. And this is 8 centimeters. Okay. So you have to figure out which is the closest to the volume of his wedge in cubic centimeters.